Learning objectives. We will discuss the following topics in this chapter. Knowledge representation KR. Formal KR, first order predicate logic. Procedural KR, rule, semantic nets, frames, conceptual dependency, scripts, and semantic web. KR issues and limitations. Using predicate logic. Syntax and semantics for FOPL. Properties of WFFs. Conversion of clausal form. Horn's clauses. Unification. Resolution principles. Deduction rules. KR issues and limitations. Important attributes. There are two attributes, instance and is-a. Those are of general importance. Since they support property inheritance, these attributes are important. Relationship among attributes. The relationship among the attributes of an object, independent of specific knowledge they encode, may hold properties like inverses, existence in an is-a hierarchy, techniques for reasoning about values, and single-valued attributes. Choosing granularity. What level should the knowledge be represented and what are the primitives? Should there be a small number or should there be a large number of low-level primitives or high-level facts? High-level facts may not be adequate for inference, while low-level primitives may require a lot of storage. Set of objects. Certain properties of objects that are true as member of a set, whereas not as an individual. Example. Consider the assertion made in the sentences. There are more sheep than people in Australia, and English speakers can be found all over the world. To describe these facts, the only way is to attach assertion to the sets representing people, sheep, and English. The reason to represent set of objects is if a property is true for all or most elements of a set, it is more efficient to associate it with the set rather than to associate it explicitly with every element of the set. This is done in different ways. In logical representation through the use of universal quantifier and in hierarchical structure where node represents sets, the inheritance propagates set-level assertion down to individual. Finding right structure. It access to right structure in order to describe a particular situation. It requires selection of an initial structure and revising the choice. While doing so, it is necessary to solve following problems. How to perform an initial selection of the most appropriate structure. How to fill in appropriate details from the current situations. How to find a better structure if the one chosen initially turns out not to be appropriate. What to do if none of the available structures is appropriate. When to create and remember a new structure. Knowledge representation KR. What is knowledge? Knowledge requires an analysis to distinguish between knowledge of how and that. Knowing how to do something. Example, how to drive a car is a procedural knowledge. Knowing that something is true or false. Example, that is the speed limit for a car on a motorway is a declarative knowledge. Knowledge category. Tacit corresponds to informal or implicit type of knowledge. Explicit means to say formal type of knowledge. Tacit knowledge. Inherited in a human being, it is embodied. difficult to articulate formally, difficult to communicate or share, hard to steal or copy, drawn from experience, action, subjective insight, explicit knowledge, exists outside a human being, it is embedded, can be articulated formally, can be shared, copied, processed, and stored, easy to steal or copy, drawn from articraft of some type of principle, procedure, process, and concepts. Knowledge progression. Knowledge is a progression that starts with limited utility of data. Data, organizing, analyzing, information, interpretation, evaluation, knowledge, understanding, principles, wisdom. The knowledge progression diagram is given here. Data is viewed as collection of disconnected facts. Knowledge representation KR. A knowledge representation KR is basically a surrogate. It is a substitute for the thing itself, used to enable an entity to determine consequences by thinking rather than acting. That is, by reasoning about the world rather than taking action for it. It is based on a set of ontological commitments. That is, an answer to the question, in what terms should I think about the world? It is a fragmented theory of intelligent reasoning, expressed in three consecutive components, namely, the representation's fundamental conception of intelligent reasoning, the set of inferences the representation sanctions, the set of inferences it recommends. It is a medium for pragmatically efficient computation. That is, thinking is accomplished in the computational environment. One contribution to this pragmatic efficiency is supplied by the guidance. A representation provides for organizing information so as to facilitate making the recommended inferences. It is a medium of human expression. That is, we say things of the world only by a language. Knowledge is a description of the world. What the system knows is determined by its competence. Representation is the way of encoding knowledge. It defines a system's performance in doing something in a better way. KR is the method used to encode knowledge based on its intelligent system. There are two major classes of knowledge representation methods that are used in AI. Logic. Methods based on mathematical logic, that is, first-order predicate calculus. Frames. Methods based on networks of nodes, which represent objects or concepts, and labeled arcs, which represent relations among nodes. Formal knowledge representation. Statements have arbitrary propositional form involving conjunctions, disjunctions, negations, and arbitrary use of quantifiers. For every man there is a woman, such that for every man. In standard predicate or first-order logic, modern variants of term logic provide the same expressive flexibility. Framework is defined by the set of axioms and the set of inference rules, such as if P and if P yields Q, then Q. The proofs are sequences of derivation steps based on these axioms and rules. For example, one can represent predicate logic and derive not every man is a philosopher if and only if there is a man like that, he is not a philosopher. For first-order logic, there are inductive as well as deductive rules, not used in mathematical theorem proving, but for uncertain reasoning, most often in AI. Procedural KR. Procedural knowledge is a mapping process between domains that specify what to do when and the representation of how to make it rather than what it is. The procedural knowledge may have inferential efficiency without inferential adequacy and acquisition efficiency. Procedural knowledge are represented as small programs that are well aware of how to do specific things, especially how to proceed. Example, a parser in a natural language has the knowledge that a noun phrase may contain articles, adjectives, and nouns. It does accordingly call routines that know how to process articles, adjectives, and nouns. Procedural KR Semantic nets. Semantic nets are used in AI to describe relationships between concepts, objects, or events. Components of a semantic net. Nodes and links. Nodes represent objects, attributes when considered as objects and values. Links represent attributes of nodes and relationships between nodes. Links have labels, the name of corresponding relation or attribute. Name corresponds to a node in a semantic net. Attributes, also called slots, filled with particular values. Example is given here. Example, in the frame for Ganesh, instance is the name of a slot and elephant is the value of the slot. Names of slots correspond to the links in semantic nets. Values of slots communicate to the nodes. Hence, each slot can be in another frame. Semantic nets. Example 2. The most usual form of semantic networks uses the links between nodes to represent is a and has relationships between objects. The example given here shows a car is a vehicle and a vehicle has wheels. This kind of relationship establishes an inheritance hierarchy in the network. It lowers down the objects in the network inheriting properties from the objects proceeding up. Procedural KR Frames. Frames are loaded with information about the types of entities and their instances. That is, all the information relevant to a particular concept is stored in a single complex entity called a frame. Frames are the decomposition of knowledge into highly modular pieces. They are generalized record structures. Knowledge consists of concepts, situations, attributes of concepts, relationship between concepts, and procedures to handle relationships as well as attributes, values. Each concept may represent as a separate frame. The attributes, the relationship between concepts, and the procedures are allotted to slots of a frame. The contents of a slot may be of any data type, numbers, strings, functions, or procedures. The frames may be linked to other frames, providing the same kind of inheritance as that provided by a semantic network. A frame-based representation is suited for object-oriented programming techniques. Example: frame-based representation of knowledge. Two frames, their slots, and the slots filled with data type are given here. Procedural KR Conceptual dependency. Knowledge enriches relationships and understanding. It is a connected web of knowledge, a network in which the linking relationships besides being prominent, they discrete bits of information. Examples of concepts: square, square root, function, area, division, linear equation, derivative, and polyhedron. By definition, conceptual knowledge cannot be learned by rote. It must be learned by thoughtful, reflective learning. Is it possible to have conceptual knowledge or understanding about something without procedural knowledge? Procedural KR Scripts. Scripts are similar to frames, except the values that fill the slots must be ordered. A script is structured representation which describes a stereotyped sequence of events in a particular context. To organize a knowledge base, scripts are used in a natural language understanding systems in terms of the situations that the system should understand. Example of a script involves the sequence of events that occur while a person drinks in a restaurant, finding a seat, reading the menu, ordering drinks from the waitstaff. Scripts can be inflexible. To deal with inflexibility, smaller modules called Memory Organization Packets (MOP) can be combined in a way that is appropriate for the situation. Using predicate logic. Conversion to clausal form. Eliminate implies reduce the scope of each not to a single term. Standardizing variables leads to each quantifier binding a unique variable. Move all quantifiers to the left without changing their relative order. Eliminate there exist. Columnization. Drop for all. Convert the formula into a conjunction of disjuncts. Create a separate clause corresponding of each conjunct. Standardize apart the variables in the set of obtained clauses. Using predicate logic. Conversion to clausal form. Example. Eliminate implies P implies Q equivalent not P or Q. Reduce the scope of each not to a single term. Not of P and Q equivalent not P or not Q. Not there exist X such that P equivalent for all X such that not P equivalent P. Standardize variables so that each quantifier binds a unique variable. For all X such that of P of X or there exist Y such that Q of Y. Move all quantifiers to the left without changing their relative order. Equivalent for all X such that there exist Y such that P of X or of Q of Y. Eliminate there exist X such that P of X equivalent to P of C. For all X such that there exist Y P of X, Y equivalent for all X such that P of X F of X. Column function. Drop for all. For all X such that P of X equivalent P of X. Convert the formula into conjunction of disjuncts. P and Q or R equivalent P or R and Q or R. Create a separate clause corresponding to each conjunct. Standardize apart the variables in the set of obtained clauses. Using predicate logic. Deduction theorem. Theorem. If H union A infers B by reduction contains no application of generalization to a variable that occurs free in A, then H. Corollary. If A is closed, H union A infers B, then H. Predicate logic. Natural reduction. Extend the set of rules we used for propositional logic with ones to handle quantifiers. Universal quantification. For all elimination, for all x dot p by p of t by x, for all E, for all introduction, for all I, for all x dot P. X0 must be arbitrary, meaning it doesn't appear outside the subproof. P must be free of x in P. Existential quantification. Exist introduction. P of T by x into P by there exists P, there exists I. Using predicate logic, Horn's clauses. For a standard form of a sentence, generalized modus ponens is a required one, called Horn clauses after the mathematician Alfred Horn. A Horn clause is a sentence of the form Q1 and Q2 and up to and Qn implies R, where each Qi and R is an atomic sentence and all variables are universally quantified. Recall that an atomic sentence is a just single predicate and does not allow negation. Normally, the universal quantifiers are implicit, not written explicitly. To refresh your memory, here is the syntax of FOL in the Backus-Naur form. Sentence, atomic sentence, sentence connective sentence, quantifier variable up to sentence, not sentence, sentence. Atomic sentence implies predicate of term, comma, or term is equal to term. Term implies constant, variable, function of term. Connective and or implies equivalent. Quantifier for all or exist. Constant A or x underscore 1 or John. Variable A or x or s. Predicate before or has color or raining. Function smelly or left leg off or plus. In order to obtain Horn classes, existing quantifiers must be eliminated using Skolemization. Example: exist x loves of John, x and loves of x, John becomes loves of John, person x, loves of person x, John. Now that we have two Horn classes which share a Skolem constant. Using predicate logic, dissolution principle. Clausal forms. Clauses are universally quantified disjunctions of literals. All variables in a class are universally quantified. For all x1 up to xn, L1 v up to vln, written as L1 v up to vln or L1 up to ln. Examples: nat of s of a, not nat of a, nat of s of a, not of nat of a. Nat a gives nat of s of a. Nat x gives nat of s of a. Nat s of x, not nat of s of x. Nat s of a gives nat s of a. We need to work with variables. Unification of two expressions or literals. Terms and instances. Consider the following atoms: P of x, f of y, b, P of z, f of w, b, alphabetic variant, P of x, f of a, b. Instance: P of g of z, f of a, b. Instance: P of c, f of a, not an instance. Group expressions do not contain any variables. Substitution. A substitution S is equal to T1 by V1 up to Tn by Vn substitutes variables V1 for terms T1. T1 does not contain V1. Applying a substitution S to an expression omega yields the expression omega S, which is omega with all occurrences of V replaced by T. P of x, f of y, b, P of z, f of w, b. S is equal to z by x, w by y. P of x, f of a, b. S is equal to a by y. P of g of z, f of a, b. S is equal to g of z by x, a by y. P of c, f of a, a. No substitution. Composing substitution. Composing substitutions S1 and S2 gives S1 S2, which is that substitution obtained by first applying S2 to the terms in S1 and adding remaining terms or variables pairs to S1. Theta is equal to g of x, y by z, a by x, b by y, c by w, d by z is equal to g of a, b by z, a by x, b by y, c by w. Apply to P of x, y, z theta gives P of a, b, g of a, b. Properties of substitution. Omega S1 into S2 is equal to omega of S1 S2. S1 S2 into S3 is equal to S1 of S2 into S3. S1 S2 is not equal to S2 S1, not commutative. Predicate calculus resolution. John Allen Robinson, 1965. Let C1 and C2 be two clauses with literals. L1 belongs to C1 and minus L2 belongs to C2, such that C1 and C2 do not contain common variables, and mu of L1, L2 is equal to theta. Then C implies C1 minus L1 union C2 minus L2 theta is a resolvent of C1 and C2. Given C such that L1 1V or 2V or up to VLM. C such that not K1 or K2 or Kn. Theta is equal to mu L1, K1. The resolvent is 12 theta V. The resolvent is L2 theta V up to VLM theta V K2 theta V up to VKN theta. Example. P of x or Q of f of x and R G of x or not Q of f of a. Standardizing the variables apart. P of x or Q of x and R G of y or not Q of f of a. Substitution. Theta is equal to a by x. Resolvent. P of a R of G of y. P of x R Q of x, y and not P of a or not R of b, z. Standardizing the variables apart. Substitution. Theta is equal to a by x. Resolvent. Q of a, y or not R of b, z. Resolution principle. A stronger version of resolution. Use more than one literal per class. P of u, P of v and not P of x, not P of y do not resolve to empty class. However, ground instances P of A and not P of A resolve to empty class. Factors. Let's C1 be a class such that there exists a substitution theta, that is, a mu of a set of literals in C1. Then C1 theta is a factor of C1. Each class is a factor of itself. Also, P of f of y, R of f of y, y is a factor of P of x, P of f of y, R of x, y, with theta is equal to f of y by x. Using predicate logic, semantics. The interpretation of a formula f in first order predicate logic consists of fixing a domain of values, not empty, D, and of an association of values for every constant respectively. Function and predicate in the formula f as follows. Every constant has an associated value in D. Every function f, the arity n, is defined by the correspondence d to the power of n implies where d to the power of n is equal to x1 up to xn or x1 epsilon d up to xn belongs to D. Every predicate of arity n is defined by the correspondence P such that d to the power n implies a, f. Using predicate logic, semantics. Interpretation, example. For all x of a, x or b of f of x and c of x implies d of x. D is equal to 1, 2. X is equal to 1. A or f and A implies f. X is equal to 2. F or A and f implies A. Using predicate logic, syntax. Be D a domain of values. A term is defined as a constant is a term with fixed value belongs to D. A variable is a term which may take values in D. If f is a function of n arguments and t1, up to tn are terms, then f of t1 up to tn is a term. All terms are generated by the application of rules 1, 2, 3. Using predicate logic, syntax schematically. Syntax schematically is represented here. Using predicate logic, unification. Unification is an algorithmic process of solving equations among symbolic expressions. Several frameworks of unification are distinguished depending on which expressions, also called terms, are allowed to occur in an equation set, also called unification problem, and which expressions are considered equal. If higher order variables representing functions are allowed in an expression, the process is called higher order unification, or else known as first order unification. If a solution is required to enable both sides of equation literally equal, the process is called syntactical unification. Otherwise, semantical or equational unification or E-unification or unification modulo theory. A solution of a unification problem is denoted by a mapping or else known as a substitution. Assigns a symbolic value to each variable of the problem's expressions. A unification algorithm should compute a given problem as a complete and minimal substitution set, that is, a set covering all its solutions, and contain no redundant members. Depending on the framework, a complete and minimal substitution set may have at most one, at most finely many, or possibly infinitely many members, or may not exist at all. Unification algorithm. There is a standard algorithm that, given for two sentences, finds their unique general substitution. There are some examples of unification. Nose of Abhinav, x is equal to likes of Abhinav, x. Nose of Abhinav, Arti. Nose of y, Aditya. Nose of y, mother of y. The unification algorithm would give the following results. Unify of nose of Abhinav, x, nose of Abhinav, Arti is equal to x by Arti. Unify of nose of Abhinav, x, nose of y, Aditya equal to x by Aditya, y by Abhinav. The substitution makes the two sentences identical. Unify of nose of Abhinav, x, nose of y, mother of y equal to y by Abhinav, x by mother of Abhinav. Notice that the substitutions always involve a variable and a ground term. Unify of nose of Abhinav, x, nose x, Anjana equal to fail. The variable x cannot have two values at the same time, so this last example fails. Another example that would always fail is unify of x, f of x is equal to fail. This fails due to the probable non-occurrence of the variable in term it is being unified with. Using predicate logic, WFFs. A well-informed formula, WFF, in first-order predicate logic is defined as the following. An atom is an WFF. If P of x is a WFF, then not P of x is WFF. If P of x and Q of x are WFFs, then P of x and Q of x, P of x or Q of x, P implies Q, and P if and only if Q are WFFs. If P of x is a WFF, then for all x P of x, there exist x P of x are WFFs. The set of all WFFs can be generated by repeatedly applying rules 1 to 4. Using predicate logic, properties of WFFs. Valid and tautology. Satisfiable. Contradiction. Equivalent formulae. A formula F is a logical consequence of a formula P. A formula F is a logical consequence of a set of formulae P1 up to Pn. Notation of logical consequence P1 up to Pn implies F. Theorem. Formula F is a logical consequence of a set of formulae P1 up to Pn if the formula P1 and Pn implies F is valid. Theorem. Formula F is a logical consequence of a set of formulae P1, up to Pn if the formula P1 and up to and Pn and not F is a contradiction. Conclusion. In this chapter, we have covered the following in detail. Knowledge representation KR. Formal KR, first order predicate logic. Procedural KR, rule, semantic nets, frames, conceptual dependency, scripts, and semantic web. K are issues and limitations. Using predicate logic. Syntax and semantics for FOPL. Properties of WFFs. Conversion of clausal form. Horn's clauses. Unification. Resolution principles. Deduction rules.